evaluate those or monetize those benefits to bring it to the economics. So when you talk about cover crops and their impact in the watershed or in the landscape, you got to think about three things. Number one, nitrogen conservation. Okay, that's how nitrogen is taken up, and then what pools of nitrogen are being taken up or interacted with by the cover crops. Okay. Number two, nitrogen release. That's very important. I don't know how many talks I've been to, and farmers say, okay, you did a good job explaining the environmental part of it, that cover crops take up nitrogen, but Doc, when am I getting the nitrogen back? So that's a common question, okay, nitrogen release. And then there's nitrogen uptake by the subsequent cash crop. How much of the nitrogen in the cash crop that was in the cover crop that was taken up is actually taken up by the cash crop that's following. So that's another big question, which also could increase the value of cover crops to adopting farmers. So this first study is a study that is funded by NREC, and it's in collaboration with Purdue and Geology and the Department of Agriculture at the Illinois State. And we're looking at the coupled effect of cover crops and nitrogen management. Okay, cover crops and nitrogen management. How does it affect what's being lost through the tile, the fate, and availability? So we have 5 treatments, and I like to start with this first one because that was the first one to get, that was the most difficult treatment to get the farmer to agree to do. Okay, so it was no nitrogen and no cover crops. And he said, why would you do that to me? Why would you make me suffer through yellow corn like that? And I said, well, how about this? How would you like to know how much nitrogen leaves your field through the tile drainage when you don't add any nitrogen to your corn? He said, you know what, that could be a good question, so let's do it. So I got him on board, so we did that. And so the next 2 treatments are split application of nitrogen, where the dominant split is in the fall, as in hydrous. We did that with or without cover crops. 4 and 5, split application where the dominant portion is in the fall, okay, because in this region, I want to understand if the timing of end application affects the ability of cover crops to scavenge nitrogen, right? So in other words, whether it's fall or spring, would it change the effectiveness or the efficacy of the cover crops, okay? And so when you think about total application, about 200 pounds per acre was added, which is equivalent to about 224 kilograms per hectare. And we used a cereal radish mixture. So this is what that field looks like. I like to show this because it kind of gives you an idea of the size and the scale that we're working on. Again, the last presentation was 1,100 acres. We're working here on units of 1.6 acres, but still large enough for 2 or 3 passes of field size equipment. Each plot, which is outlined in blue, consisted of 3 tile laterals, 45 feet apart, and they converged at the yellow box, which is this tile monitoring station, solar panel driven, and automated samplers. The graduate students like that. So that used to be a graduate student right there. They just sit there at the tile and take samples whenever it rains, right? But now we replace that graduate student with a machine, and it takes water samples from the tile, and then we're able to measure that water, okay? And then now we know the consequence of the nitrogen management on the surface. So I like to show this field scale. Field scale, and we're not out hand cranking, cover crops, cereal onto the soil. We actually have a retrofitted Hagie sprayer that drops the cover crop seed at the base of growing corn, standing corn and soybean. Okay, and you can see here our rates and the timing of that application, that planting date. So I have this thing, good, bad, ugly, okay? I thought you could relate to that. So the good, we got good cover crop growth, we got good nitrogen scavenging, we got good nutrient loss reduction, decent possibility of some nitrogen cycling, and then we had a good soybean yield, okay? So this is cover crop end uptake. So in other words, how much of the nitrogen was actually interacted with and taken up by the cover crop. And so what we found, the general trend is that 14 to 16, when the weather pattern was normal, and it's colder in the fall than it is in the spring, you got more growth and uptake in the spring. Now in 15, we were abnormal. So you had more fall growth. We had just as much fall growth and then uptake in the fall versus the spring. And I thought that was significant. And it plays to the fact that mixtures are sometimes better than just having one type of cover crop species planted. So in the fall, when you get a lot of growth, we had that radish cereal mixture. The radish took over, okay? Only 8% of the mix, but accounted for 50% of the nitrogen uptake, which was significant. And then when the radish, it finally gets cold and the radish terminates, winter terminates, the cereal takes over, and then the other 50% of that uptake occurs mainly in the spring. So on average, about 60 pounds per acre taken up over 3 years. That equates to about 30% of the equivalent mass of nitrogen that the farmer would apply. So cover crops would not take up the entire rate of nitrogen that you put down, only about 30%, okay? So the idea was, this is the farm before we got there, and we added cover crops. How is it going to affect the nitrogen loss through the tile drainage? That's what we're testing. So the first thing that I want to show is that when you cover crop, and that cover crop is growing, it needs nitrogen to grow, and it is scavenging nitrogen from the soil at a deeper depth than you think. So here's the surface at 0 centimeters, and this is where we stop sampling at 80 centimeters, which is 2.5 feet, which is equivalent to, let's say, a foot away from the tile in that area. Okay? So if nitrogen is here, by the time you plant here, by the time that root system of the corn or soybean gets to the point where it grows 2.5 feet, that nitrogen is in the tile and halfway to the Gulf of Mexico. Okay? So when you apply cover crops, what we see is that these two lines are the fall and spring without cover crops. This gray line is the fall with cover crops. This is the zero control, and this is spring without cover crops. So there's at lower depths, you can see that the cover crops reduce the nitrogen that was close to the tile, which is susceptible to being lost. Okay. We go to the next step, and here's the water quality. So basically, the green lines, the triangle and the squares, are spring and fall cover cropped plots or treatments. And the black lines are spring and fall without cover crops. And here's the red line, that's the zero control. And everybody's like, Doc, you're wacky, because there's no way that you could lose more nitrogen over 2 years with the zero control when you add no nitrogen compared to when you did add 200 units of nitrogen in these 4 treatments. Well, we did. We lost just as much when we didn't apply nitrogen. Now, hypothesis number 1, organic matter, 3.4% on average. So you're going to get some nitrogen that's being put into the soil solution susceptible to being lost from the organic matter. Number 2, how does corn look when you don't fertilize it? Unhealthy. It's unhealthy, right? It's yellow, right? How does corn take up nitrogen? Through a trans-evaporitional stream. So if that plant's not healthy, it's not going to put a demand on the water in solution, so it's not putting a demand on the nitrogen in solution, so that nitrogen is free to move, okay? And so with the combination of those two, and you're not removing as much because you're not getting the uptake or the yield. So with the combination of those 3 hypotheses, we think that's why we get equal or greater nitrogen loss when we don't apply nitrogen compared to when we do. But on average, when you don't apply nitrogen, whether, and it doesn't make a difference whether it's fall or spring, there was not a significant difference between the 2, fall and spring, you lose about 50 pounds per acre per year. You decide to cover crop, and that changes to about 27 pounds, which is a 46% reduction. Okay, so this is on a field scale. Dr. Raleigh just showed something similar on a watershed scale. So directionally, cover crops is behaving the same when you integrate them across scale, which is important. So that means that I can do something here and kind of predict what could happen on a larger scale, okay? Now, the question is do we have monster cover crops doing this? Just cover crops that look like oak trees? No, right? What we had was, on average, 1,200 pounds per acre, okay? 1,200 pounds per acre, that's what that looks like. 1,200 pounds per acre terminated 2 to 3 weeks before planting. We were able to get this kind of reduction. So you don't need cover crops up to your waist. Why create that headache, right? So one question that we're trying to examine is how much do you need to actually get the environmental reduction, but yet be productive agronomically, okay? So just a further breakdown. One of the things that was surprising to us was when you had fall versus spring without cover crops, there was no difference in the loss. And that's at that field with that organic matter over these particular years, okay? I'm not saying that happens everywhere, but when you add cover crops to that mix, you get a 42% reduction. So the cover crops is moving the needle environmentally when you add them to the system. When you compare spring, watch this, compare spring nitrogen versus fall with cover crops. Leave the nitrogen in fall, add cover crops. You get a 50% difference, a reduction in the nitrogen loss. Now, I'm not advocating for fall applied nitrogen, but what this is showing simply is that despite, irrespective of the nitrogen application timing, cover crops are effective. So across the spectrum of the upper Mississippi River Basin, Ohio, Wisconsin, Michigan, you name it, if you can get the cover crop to grow, you get about 1,200 pounds per acre. It's going to be effective whether you are putting down swine manure in the fall or in hybris or moving all of your applications to the spring. It's effective, okay? So this is the last point of the good, all right? Soybean yields are very good, not affected by cover crops, okay? So now, we move to the next step. And when I say bad for me is exciting. Bad for me is exciting because I get to make the mistakes that you shouldn't make as farmers and CCAs, right? So I get to make this mistake and take it to the lab and unpack it and dissect it and then come back to venues like this and explain what I did in the worst case scenario, okay? So cereal rye did impact corn yield and the uptake efficiency. So this is a challenge. We need to move to adaptive management. We know cereal rye can take up nitrogen. Great. What's next? We need to get equal or greater yield, okay? So first year, not that bad. And we do see that the zero control, we didn't have contamination. And so if we did, this would be higher. We didn't have contamination. Corn yields were not significantly different other than spring versus spring with cover crops, okay? 2017, bad. We didn't get it done as far as the agronomics. Now, one thing to note is that even though we terminated 2.5 weeks before planting, we had the highest, this was a very wet and warm spring, and we had the highest biomass at the site in this year. So about 2,300 kilograms per hectare, which is about, I think that's about close to 2,200 pounds per acre. That's a lot. Okay, that's about 800 or so pounds per acre of carbon. And carbon could cause immobilization. That's something that farmers have to think about when they're cover cropping. So we did this without adding starter, right? So we did corn following cereal rye without adding starter. I do not recommend that you go home and do that. Don't go home and do that. Okay, add the starter so that you can compensate for the immobilization that's occurring. So let me break this down and unpack it. So when we looked at nitrogen uptake, from V6 to V12, no significant difference. In fact, they're identical as far as uptake for that corn following cereal rye. And there was no difference whether you fall applied or spring applied. But then as we convert, the plant converts from vegetative to reproductive growth, you start seeing a gap forming. And we call it the end gap. That's the challenge. That's what I dream about, right? I want to reduce the end gap, okay? So we say, why is this happening? Could I close that gap with start? Possibly. Could I close that gap with early pre-plant, early spring, right at termination? Possibly. So these are things that we're exploring. But we decided to look at the nitrogen uptake efficiency. About 30% reduction, and this is 2 years, we saw almost identical results. Carbon from the cereal is causing immobilization in the soil, meaning that the microbes are going to the soil and stealing nitrogen from the soil solution to metabolize or to break down or to decompose the cereal residue. Now, while that's happening, the corn is like, hey, that's my nitrogen, leave it alone. But there are 7 million or so microbes per teaspoon of soil. So who's going to win that tug of war? The microbes. So we dug a little deeper, went down into the soil microbiome. And so on this axis is the number of unique bacteria, right? And then we looked at sample across growth stage. And so when you have something like hairy vetch with a low C/N ratio, you get a spike in diversity, you get a spike in the mass of the microorganisms early on, VE emerges. But when you have something like cereal that has a high C/N ratio, that spike does not come early. It actually comes when you side rest, right at V6. So we just discovered this. So really what's happening is that there's a tug of war. We've created a competitive sink for nitrogen when we added the carbon that comes from the cover crop. So we have to adaptively manage that. The corn is struggling against the soil microbes and they're fighting over nitrogen. So how do you deal with that? Okay? So we need adaptive management. So we did another study. These things are kind of going on at the same time, where we looked at different cover crop selections and how they impacted corn yield. Okay? And this is 16, this is 17. And what we noticed is that wherever you had cereal, compared to the control, you were significantly less. But then when you had this mixture, and I'm gonna tell you what's in that mix, or if you do a double rotation, rotate the cover crops as you rotate the cash crop. So put a low C/N ratio cover crop before corn, like radish oats. And then come back when you rotate into soybeans after that corn, then you can afford to put cereal because soybeans can make their own nitrogen through fixation. We found it over 2 years. That's pretty decent, right? This is the control. This is hairy vetch. This is a legume. You expect that. But then there's cereal in this rotation, right? But you're getting close to equal yields, okay? What about corn on corn? Okay, so in the big mix, there's hairy vetch, there was rape, there was radish, and cereal. But when we went to soybeans, we only had cereal. So we saw some improvement here. Here's still an opportunity. We need to learn more about corn following cereal. If you go continuous corn, same thing applies. Okay, where you had cereal, you had a reduction. Where you have those mixes with the low C/N ratio before the residue for the corn, basically equal. Okay, in both years, basically equal. Okay, so here's another management strategy that I found out of Iowa. Basically, they varied termination 1 day before planting versus 21 days before planting. And then, so that caused a significant increase, right? So then, even within, when you do a 21-day before planting termination, you're still getting more yield when you do strip till prior to, early spring prior to termination. Let's say a week prior to termination. It made a difference. Why? Because you're putting down the nitrogen that the microbes will need to process the carbon from the cereal. And you terminate it on time. Most likely, you got pretty decent reductions, at least 30% from the tile. So now you put the farmer in a win-win situation. Environmentally, footprint is smaller. Agronomically, I'm still good, I'm putting bread on the table. That's what we need to do. Okay, last study, this is an end tracking study. So the challenge is seed rye because it is done. You can throw it from an airplane, it'll grow. Throw it from a high boy, it'll grow. Drill it, it'll grow. But we can't get corn to grow behind it. So we want to track nitrogen into the seed rye, into the soil after decomposition, and then back into the corn to see what we get. So basically, what we found so far, this is what we found so far. We're doing this in Illinois and we're doing this in Indiana simultaneously. We found that at about V6 for corn, 7% of the nitrogen in the corn came from the seed rye that was terminated before. And you can see for soybeans it's only 3.2%. There's a dilution effect at R1 because that plant is bigger. It took up more nitrogen from the soil and from the fertilizer. So only 2.5% was in the corn that came from the seed rye. So from termination, from the growth VE of that corn to R1, a total pounds that came from the seed rye that's in the corn was 3 pounds, and for soybean, 2 pounds. And so I'm going to summarize and take questions if I have time. So basically on a plot scale, on average, the cover crop's going to interact with about 30% of the mass of fertilizer that's applied. Cover crops had about a 40 to 50% reduction despite application timing, and that's quite a bit higher than the neutral loss reduction strategy that said on average, based on literature, was about 30%. When you look at crop yield improvements, we have to do some adaptive management. We need a double rotation. Rotate your cover crops and your cash crops together. And about total 3 pounds of nitrogen from the seed rye was in the corn at R1. And so with that, I'll take any questions that you may have.